Thank you for the kind introduction, Mr. Murthy. I really appreciate that. Without further ado, let's get into the topic. So we are going to present on the topic of multi-tiered digital twins with what-if analysis and predictions on March 17th during the conference. So basically, the talk is about supply chains as complex systems, how you can model them, and if they're modeled correctly, how you can do some pretty proactive and cutting edge analytics and predictive technologies on top. So supply chains are complex systems. This is a realization that kind of is like permeating across the industry now. They are not simple systems, they're complex, but they're complex in three different ways, right? So they're complex in one way, which is that they are networks, very big, complex networks of flows. What is flowing along the edges of that network? You have physical things like products, spare parts, raw materials, electricity, water, things like that. All those things are needed in the manufacturing process. So obviously there's a physicality to that flow, but there is also the notion that risks of various kinds also flow through this network. And that means that when something happens, good or bad, at one side of the network, it can, in some cases, actually propagate, literally flow along the network, that risk, and kind of affect really far off entities, which may not be even aware that they were exposed to that risk, right? So that's the first aspect of being a big complex system. The second aspect, or the second way in which supply chains are very big and complex, is that they're big state machines, and that primarily happens because each of these nodes in the network, they are not memoryless. They have a memory. They have some kind of statefulness. And some of the statefulness is just because of physicality. Again, there is an inventory being carried from day to day. There's production that's happening. These are not things that can change abruptly on a dime. There's a statefulness to that, right? But the statefulness also comes in because of policies, inventory policies, shipping policies, and things like that, which are also induce a kind of statefulness. Now, obviously, the local state of each of these nodes may be, modest, moderately small, but when you think of the combined global state of this entire supply chain, it's a very humongous state vector. It can have millions of dimensions, and predicting where that state will evolve, controlling it, keeping it stable is not a mean task. So that dynamical state machine view becomes important. And then the last aspect is that and this is a modern way of thinking of supply chains, is that supply chains are games. They're in particular multiplayer games. They are multiplayer because there are various stakeholders like customers, suppliers, manufacturers, service providers, and they are not a single business. They are different distinct businesses. They have their own business KPIs which they are trying to maximize. And so in that sense, it can be a competitive game, but it can also be collaborative in certain circumstances. So given that supply chains are complex in this very specific three set of ways, you have to kind of watch out for certain things that complex systems are known to do. If they're designed badly, there are certain things that happen with complex systems which are very nasty behaviors, right? So one is this extreme sensitivity to disruption and disruption cascades. And in supply chain, that's often called as bullwhip effect, right? So you make some change, or there is some kind of disruption at one side of the network, and then that risk or the disruption kind of cascades and affects like other faraway entities, this kind of behavior, right? The other thing that can happen in a poorly designed complex system is that it can actually kind of veer into proper chaotic behavior in a mathematical sense. There are these regions of parameter space which are called chaotic attractors, and they have this property that very nearby points in that attractor can lead to very different outcomes and very different trajectories. And so a deterministic system can start behaving almost like as if it is quasi random. It is random for all practical purposes, and that is a very sobering thought. How can a physical system like a supply chain start behaving like a random system, right? Random behavior system. And there is some really good literature on that coming up in the recent years. And the last one, obviously, is that because it's a multiplayer game, it can actually lead to non-cooperation. And in the worst case, it can actually lead to malicious behavior, right? People really trying to take each other down. Now, there's a flip side to this, that a properly designed and a well orchestrated and well incentivized supply chain can actually have the duals of this. It can actually do good in all these aspects. So it can actually show aspects of self-organization and self-healing. And this happens in like a very well-known complex system that we all know, which is our body, right? Living systems are complex systems, and they have these properties. Complex system also, when properly designed, have this notion of built-in redundancy, which is, for example, in wireless sensor networks, this is used very often, that you take off a few nodes of the network, nothing happens. The network keeps functioning as if nothing happened, right? So really good property. And then, of course, if you properly incentivize the game of supply chain, you can actually cause cooperation. And in fact, you can cause co-optimization, right? And this notion that a game need not be competitive, you can have an entirely cooperative game is well known in game theory, but it's something that supply chain domain has to understand, that it doesn't have to be a zero-sum game. Actually, everybody can benefit. It can be a fully cooperative game. So with these kind of thoughts in mind, the next question arises is that what kind of modeling paradigm, what kind of modeling construct should we use so that we can actually do justice to all these three ways in which supply chains are complex? And the industry seems to be kind of getting behind this idea of digital twin as that modeling paradigm. And the reason that digital twins are so interesting is that they act as a semantic representation of the physical world. And obviously it's a model, so it's not going to be as complex as the physical thing. If the model happens to be as complex as the physical thing, then it's of no use, right? So it's an approximation, so it kind of reduces things and represents them more simply than they are actually in physicality, but it retains the richness and the flavor so that you can do adequate, decision making on top of that. But it acts as a semantic layer, and it allows the consumers, which are like AI developers, scientists, and even like end users, to actually semantically query and get hold of the knowledge without actually worrying about how the knowledge is being accreted and connected across all the different silos and rooms of the house of the business, right? So from marketing, sales, inventory, warehouse management, production, and so on, how all this data can be brought together. And even, in fact, even from across business boundaries, how you can get data from your suppliers and from your customers, and how you can all convert that into knowledge which is connected into this singular representation. So digital twins are not like new. The IoT world has been talking about this for some time. But the notion that you can use digital twins to represent something that is non-physical, something that is like more business process, like what happens in supply chain, is actually quite a new, novel application. And Gartner has done a fair bit of like publication on these open papers. They have defined what they mean by a digital twin for supply chain, but so have some of the other analysts. And I get the feeling that this is kind of like becoming a convergence in industry thinking around how you should model and represent supply chains for doing analytics and AI. So having said that, now what are the cool things you can do with this digital twin? You have a great model. It has the ability to give you knowledge that you can query out and use it to build models, do predictions, simulations, and so forth. But what are the actual use cases where you can really make a big difference with that? For that, I'll hand it over to Mayank, and he can walk us through a couple of interesting examples. Mayank, are you there?
Thank you, Anand. Yeah. So as Anand mentioned, a digital twin empowers you to collect data from various business processes across different departments, such as logistics, procurement, and manufacturing, and then breaks down the silos between these data sets and brings together a unified representation of the entire supply chain network. In addition, you can enrich this data with external signals such as demand sensing, risk, and financial signals, which could be extracted from sources such as news, web search, and other external data sets. This holistic view of internal data coupled with the external signals allows you to build more accurate models, such as forecasting customer demand or forecasting risk at each node in the supply chain. Such models then can feed into larger supply chain multi-echelon optimizations, such as inventory allocation. And these can be tuned such that they optimize the appropriate KPIs that a business wants to optimize for a particular scenario. Now, if we go to the next slide, while such models are great to capture and optimize the business, in practice, supply chains are, as Anand elaborated on, very chaotic systems, and there are possibilities of exogenous events and disruptions at any time. These can range from situations like demand for a particular product doubling overnight, a supplier going bankrupt, or even something like a shipment getting stuck in the Suez Canal. So a digital twin at this stage empowers you to simulate such scenarios and measure the impact of them on the supply chain and get appropriate recommendations to build resilience in the supply chain for these unplanned scenarios. The cycle obviously then continues as data generated from these new business processes you implement gets captured, gets fed back into the twin, and you continuously go into a system of business process data capture, modeling, simulations, and actions. So, in the talk during the conference, we will go into details of how a sample inventory allocation scenario, such as making products to stock or building them on incoming orders, can be tackled by such a system. Starting with a baseline policy based on ABC XYZ analysis of products, we can leverage optimization techniques such as simulated annealing, and arrive at an optimal policy, which fundamentally improves on metrics and fitness values, but then also empowers you to get recommendations for what if scenarios like changing customer demand or meeting new customer SLAs. This dashboard shows how, for each of these policies, how relevant KPIs are affected and recommendations for how many products to make to stock or build to order.
Okay. Thank you, Mike. That was awesome. We also want to give a quick shout out to the fact that some of our colleagues, Tedway and Danny, as well as some other industry invitees, Ajay, they're going to do a panel on AI in supply chain. It's on the same day, March 17th. So, you are welcome to also attend that one. It should be a great discussion forum. And with that, we'll end.
So, yeah, this is Lakshmi, as Dr. Murthy introduced me. So, yeah, my talk is going to be about how do you start with the model development. The next slide.
Yeah, she will move it.
Yeah.
Lena will do. Yeah.
So yeah, the motive of my talk is actually that if you are an ML practitioner, or if you work in a team where you work with ML practitioners like data scientists or machine learning engineers, and you have identified a problem space that could be benefited by developing an ML model. So when you are in that situation, so I'm going to be giving a talk about how do you go about it? What are the steps you'll be following, and what are the issues you'll be facing at every step? So for this particular talk, since it is like a very wide spectrum, I won't be talking about deep learning techniques or unsupervised learning or anything reinforcement learning. So I'll start with the use case of when developing a supervised learning, using a simple machine learning algorithm, what are the things that you'll be following? And next, yeah.
Move, yeah.
Yeah, so let's do a quick recap of machine learning model development. There are different data sources, and from these different data sources, you will be collecting all the samples that is required. And the next step will be to identify what are the meaningful features of this problem and how do you do some feature transformations on it. The features should be actually representative of the problem you're trying to solve. And the third step is how do you experiment with different algorithms, classification, clustering, or regression models, or like anything, and how do you fine tune the parameters, and then you will be launching the model you have developed in production. So next, so the first step is you go at different data sources and then you start the data collection, right? And here I'm going to be to understand what is the data and like to learn the problems you will face at data collection. Let's first categorize the data into 3 different categories. So the first thing is behavior data. So it is a class of data which we refer as behavior data, is that which describes a particular users. How did they behave when they are using a product? For example, how did I behave when using Google search, and how did I behave when using YouTube? And the second category is feedback data. So this is like the specific data that is collected by we as a service owners or product owners explicitly collect by reaching out to a particular customer asking for, hey, how did we perform, or what did you miss, or what did we miss? And so, and the third category is when neither of the data is directly available to you, or like any data set that you want to build a model is not available. And then you go ahead and you synthesize the own data, like where you start with a manual data synthesis, like you ask, for example, going and asking users to write down a particular text so that you can have the handwritten data for modeling, and or like asking users to spell out something so that you have the audio data for modeling. And so like those that will fall under the category of synthetic data. So instead of calling them as like video, image, and text, why have I given this weird classification? You must be thinking, right? So because by classifying them with the origin of the data is being collected, what I'm trying to do here is we're trying to generalize the problems that they will all be facing in common under a single umbrella. So you can go to the next. So first, trying to understand what are the common skills required in collecting the data. The first thing will be data ingestion pipelines. So A data engineering expert who knows a lot of SQL will be developing the SQL pipelines to collect the data, or in any language. Usually the data set won't be available to them in a single source. So they will have to manipulate different data sets, do some join operations, and collect and develop a pipeline so that, and schedule certain things in certain ways so that you always have constant access to the data. The second thing is product research, or the domain knowledge and so on. So usually the product managers of the team or the company, they will have this information of what is going to be useful. They will think from the point of the customer, and they are going to let you know that what is the useful information and how you have to be dealing with. And the third thing definitely is software engineering. So they have this skills on how to deal with big data, how do you deal with distributed systems and so on. So as I mentioned before, the 3 different kinds of data, the skills required will vary in certain extent, and they will influence the data collection process for the ML practitioners in different way. And what is the influence? Next. So for example, as an ML practitioner or a data scientist, you heavily rely that the data collected and given to you is representative of the problem, and all you have is some random set of samples in your hand. So the randomization is the key here. But what usually happens in the data collection is that because of some engineering trick they employed, or the data engineer designed it in certain way, or the product manager feels something is going to be quicker in certain way, the data often travels or comes with a bias in it. For example, when collecting the feedback data, there is a tendency to collect only after thinking that we failed to deliver something. But by just using that data to model a problem, it is not exactly going to be representative of the entire use case, right? So that is one. And trying to be frugal with by the feedback collection service or the data collection service, and always trying to collect feedback during one particular time of the day, or only constantly monitoring one set of customers, man saying that, hey, let's model the whole system by trying to represent how prime Amazon customers will purchase from Amazon. It is not exactly going to represent all the customers, right? So randomization, or having ensured that the data is representative of all the instances we are trying to model or trying to score at the time of the model training is very important. So how do we do that? I'll go into more details during the conference, but this is the problem you need to know that we'll be facing. And next, please. So we have collected the data and it is in the perfect bundle we want. So the next step is going to be feature extraction. Next. So the first problem which we all face during the initial stages of machine learning design or modeling is, we know the problem and we know what we want to solve, and what exactly constitutes such features. How do we go about it? We can be creative and we can get everything that we want, but how do we start and where do we start is a primary question. So when designing the feature extractor, let's start with a template saying that these are the 4 categories in which we can think of what features will be necessary. The first thing is profiling, saying that if we are trying to model something for a customer or for any entity, that we are trying to make them into collect some profile features related to them. For example, what is the gender of the customer and what is the age group of the customer. They can represent about what is your shopping style is going to look like and so on. So they form into a category called profiling. And the second thing is aggregating behavior. So basically that how did a particular customer or a user behave when they are using a particular product for a particular period of time. So basically that how many Facebook videos did I like yesterday represents that how my my behavior, and if Facebook has to use my data into modeling something, they're going to go over this aggregated the number of videos I liked for a particular category for a particular period of time. And so the third category is density features. So if you have something about a customer, like an image or about a text information or anything in which you want to condense it as a feature, you go for density features. A very common example is in NLP, what you call as bag of words features is a form of representing density features. You're condensing the information as the audio or visual representation or a textual representations into some numeric values so that you can take that numbers into your model. And the third thing is contextual features, like something you look around and you extract either of the same set of features above for so that you can tell your model what to do. So this is a template you can remember for going about how am I going to start with the feature extraction for a particular problem. I mean, there will be a lot depending on the use case, but this is a common template you can carry into or like think about scaling into any problem. Next, please. So yeah, we extract the features. The next thing will be like, we want to do some transformations on top of it. An example I've given here is binning. Binning is a common transformations we do for certain features when we want to convert them from a particular number into category. This is how a binning of a particular like a data set which has the age of the customer will look like before and after. The first image is about how a histogram representation, where if a particular customer exists for that of that age exists, then I'm calling it as marked it as a bin 1. Otherwise, it is like binned as 0. So, and the second thing is about binning with respect to age. How many number of customers exist for this particular age group, less than 20 and 20 to 30 and 30 to 40. So this is an example of feature transformation, and there is lots of feature transformation techniques we can use, like dimensionality reduction and so on, and many things. So what do we have to think when we are trying to do any type of feature extraction or like feature transformation is that, am I making the information easy for the model to use? So basically, if all the features of all the data instances are the same or they are all completely different, then the model is probably going to throw it away, or like it is not going to turn into any meaningful representation. So what is the intent of a scientist when they are actually trying to do the feature transformation is that this information is getting more clearer or more usable for the model, or like so that we can improve the accuracy by this feature representation, or after transforming this feature into this particular representation. So feature transformations can come in two ways. One thing is either from our domain knowledge or by using some statistical techniques. Here we have a domain knowledge. In this example I've shown in the slide, it's coming from a domain knowledge that certain category of age groups are going to act certain like in a certain way, for which is what we are trying to model. For example, if in Amazon, let's say like people of the age group 20 to 30 are going to be more interested in the fashion products, then representing, rather than just giving age as a number, then just giving the category along with the label of what if they have purchased or if they have been interested in something or not, it is going to be a way much better representation in the model. Next, please. And the third step is obviously we use all this information to train the model. So what are the key things we ask ourselves when starting with the model training before choosing what is the model to train is that, next please.
Try to conclude.
Yeah, this is the conclusion slide, Dr. Murthy, actually.
Good.
Yeah. So we asked a few questions that what is the size of the data set? How many instances do I have? How many features do I have? And what is the number of output classes do I have? They heavily influence on or even saying reducing the search space of whatever model algorithms we can choose into a certain category. And how is the class distribution like? Is it balanced or imbalanced, or like how is it looking and so on? And the next thing is what the features and the output, like how are they looking like? Do features interact? Do I expect the features to interact with one another to obtain something about the model? And design of the model itself. Sometimes it is worth to ask the question to yourself that is the machine learning, do I need a machine learning model for this problem for all data instances, or am I targeting only a ML model for very few of the instances? Or sometimes can a rule-based model can be sufficient because I've studied the features and this is what I'm learning. Can I not use a model here? Is also sometimes a worthwhile question to ask before doing the model training. we can discuss all this in detail at the conference. And yeah, I hereby conclude, and thank you.
Yeah, thank you. I know we're really behind time, so I'll try to make up a little bit of it, but I did want to talk about
Don't worry about it.
the
Last
approach.
speaker, you can go ahead with whatever time you need.
Sure. So I want to talk about what I'll be talking about. I do focus in the financial monitoring space, primarily anti-money laundering, but also looking at sanction screening, know your customer issues, as well as market surveillance issues. There's a lot of cross-cutting concerns in those areas. But specifically in State Street, over the past couple of years, we have been on a journey to transition from rules-based monitoring to machine learning-based monitoring. And that implementation has gone very successfully. We've seen some real reductions of our false positive rate and the ability to identify risks that we were not previously able to identify. So I talked about that in a previous conference before we did it, and now we have done it. And in this upcoming conference, what I would like to talk about are some of the practical challenges that we face in doing so. Now, as I've said just now, we've had really excellent results. That said, this is hard work. It's interesting work. It's subject to a lot of scrutiny by regulators, which happens across different sectors, but certainly in the financial sector, we are very heavily regulated. So regulatory concerns are always foremost for us. So we've seen a lot of practical challenges, and I think since this is an area that continues to develop, in addition to talking through some of those practical challenges, I want to challenge the participants to think about how we interact with regulators and how, whether it's in this sector or others, we can address some of the challenges in using machine learning to push forward the evolution of the sector, to address some of those issues, but also to make it so that we can harness the advantages as well. So just briefly talking about some of the practical challenges with machine learning, and some of the other intro presentations touched on this. We have supervised versus unsupervised options. They have their pros and cons. There are different algorithms that can be more or less effective. But one thing that covers all of them is that from a regulatory perspective, these are considered to be models, and we have to be able to show the effectiveness of those models. We also have to be able to show how they actually work. So that's addressing the so-called black box problem. We cannot have black boxes where we don't understand how the models are operating in a regulatory space. Also, our data has a lot of quality issues. That's nothing new. It's rampant across the financial sector. For multiple reasons. We pull from a lot of different data sources. When we're talking about financial monitoring, we're at the bottom of the stream, taking whatever data might be available in the rest of the bank. That data may not talk to each other. It may have gaps, it may be inconsistent. Actually, it's all of those things all the time. So that means that when we think about how we manage the models over time, we have to look very carefully at retraining and also at the concept of tuning. Now, even with rules-based models, those are subject to tuning requirements, but it's a whole new ballgame when we're talking about machine learning. And so I want to touch upon some of the issues there and how we're confronting them now and how we want to see that evolve into the future. Also, with regard to financial monitoring, we spend a lot of resources all the time in the major institutions in looking at alerts that may have nothing to do with actual risks, the high false positive rates. And we're attacking that with machine learning models, but there's a lot further that we can go. Because the false positive rates continue to be very high. But I think we need to think about how we describe risk and what's low risk versus high risk and where we should be concentrating our efforts. So this has practical implications for how we set up our models, but it also has implications for how we interact with regulators. Regulatory approach to machine learning model usage is built out. Those of us who are in the forefront of working in the to engage with regulators on shifting toward a greater emphasis on high-risk activities. And that are better. It will also make us more efficient and have a positive impact potentially on access to financial services, because compliance activities won't serve as such a barrier, particularly in terms of cost to others participating, whether it's in the wealthy countries or around the globe in less wealthy locations. Then I also wanted to touch briefly on some considerations for the future. Blocked out in different ways in the large financial institutions, and we're going to be expected to monitor it. We're actually starting that up in State Street now, and that's going to be very interesting. It presents both some technical challenges as well as some paradigm challenges, because it's really a different way of processing data. And then also we have dependencies that are outside of ourselves, such as everybody wants data scientists. So that's going to impact across the board. And then we're going to have some expectations coming from regulators that we monitor more in real time. That exacerbates all the challenges that I've talked about. We're going to be expected to take in more data and not just structured data. So these are technical challenges that we're going to have to solve. And then again, in the regulatory space, the regulations around what data can be shared in what ways and when is becoming more and more complex, and have to be able to account for that, both in terms of how we model and what data is applicable for a given model, permissible for a given model, and what it's not. So a lot of interesting things happening in this space, and I'm hoping to, as I said, really focus on practical aspects, but challenge the audience members also to think about what role they can play in evolving this sector.